If I graph this, what's the graph going to look like? It's going to be a line. That's all I asked for. It's going to look something like that. How we graph it, we use certain methods. Right side up, upside down. Okay. Yeah. It's going to be a double parabola. It's going to look something like this. Okay. So we haven't seen these before. We haven't graphed ones that have had x cubed or x to the fourth or x to the fifth in them. Okay. Those are called polynomial functions, and those are what we're going to be talking about in this unit. So it's another type of graph, okay, that we're going to be looking at. And we're going to look at, first of all, the properties of them, okay? Then we're going to talk about how to graph them. And then we're going to talk about how to find the equations given the graphs, just like we did in Unit 1, just like we did in Unit 2. But the method's a little different. The only thing I want to talk about today in this lesson is just basically some vocabulary and what certain polynomial functions look like. So if we want to get really mathy, this is how a polynomial expression would be, or polynomial function would be expressed. But that's very confusing. Basically, it's going to look like you're going to have y equals, and then there could be some number x to the, it could be fifth, and then plus, and then maybe another number, 7x to the fourth, and then maybe you have a minus 3x to the third. Basically, it's taking this form. Okay? So what do all these letters mean in this fancy notation? N just represents the integers. Or sorry, the exponents. Okay? So n could be 5, which means this one is 4, which means the next one could be 3, the next one could be 2, then 1, and then some number. X is a variable. These numbers in front, they're real numbers, we call them. What are real numbers? Any number, basically any number that you have worked with right now. Whole numbers, integers, fractions, decimals, irrational numbers like pi, numbers that don't repeat or don't end. Okay, all of those are part of the real numbers. Every polynomial function has a degree. And how do we find the degree of the polynomial? We look for the highest exponent in the polynomial. So in that previous one I gave you, the degree would have been 4, because the highest exponent was x to the fourth. In a quadratic, the degree is 2, because the highest exponent is 2. The number in front of the variable with the leading exponents is called the leading coefficient. And the number at the very end that doesn't have a variable attached to it, that's just called a constant number. It doesn't change. So like the number 5 is a constant. 5x is not a constant because it could change depending on what x is. So do you have to be able to define these things? No. But you should be familiar with how to recognize them. So our first example is basically we're going to look at different functions, and we have to determine whether they're polynomial functions or not. If it is one, we want to state the degree, the leading coefficient, and the constant. So the first one. Remember, the exponent, n, has to be a non-negative integer. Is the exponent in this one a non-negative integer? Is it a number? No, it's a variable. So not a polynomial. Because the exponent is a variable. The exponents can never be variables, they can never be fractions, they can never be negative numbers. Okay? They have to be like 0, 1, 2, 3, 4, 5, and they can keep going forever. Like you could have 500,000 as an exponent, but you can't have negative 500,000. How about the next one? Are the exponents all whole numbers? Yeah. Look at the numbers that we see there. They're all real numbers. Looks good. It's a polynomial. So because it's a polynomial, I want to know the degree, the leading coefficient, and the constant. And here's how you find them. What's the highest exponent you see? That's the degree. What is the number in front of the variable with the highest exponent? That's the leading coefficient. What is the number that has no variable attached to it? Be careful. Negative 17. That's it. How about the next one? Not a polynomial. Why? Negative exponents. Okay. How about the next one? What seems to be the problem in this one? Yeah, that square root. I mean, this is fine. Nothing wrong with that. But do you remember how to write a square root as an exponent? Square root of x, and I know we learned this in grade 10, is the same as x to the square root of x also means a little 2 in front. Is that x to the, no, not x squared. X squared and square root are different things. It's a fraction exponent. X to the 1/2. Like the cube root of a number is the same as that number to the third. The square root of a number is the same as that number to the half. So is this a polynomial? Sure isn't. Anti-fraction exponents. Not a polynomial. Fraction exponents. It's not allowed. The exponents have to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and counting up forever. No decimals, no fractions, no negatives, no variables. Be careful, sometimes they might be in different order. Like in E. What's potentially throwing you off? The pi, right? Is the pi a real number? Can I write pi as a decimal that repeats or ends or never repeats or never ends? Yeah, so it's okay. It's okay to have pi. So this is a polynomial, but it's in a mixed up order. So you got to be careful how you name these things. What's the degree? 5. Highest exponent that you see, doesn't matter where it's located. And as soon as you got the degree, the highest exponent, you should be able to find the lead coefficient. Pi, that's the number in front. The constant? 7. That's the one that doesn't have a variable attached. Oh, this one? Yeah, this one is it? Oh, it's a bit of a weird one. You don't necessarily have to have exponents. It could still be. And you don't necessarily have to have variables. So this actually is one. But it's an extremely simple one. And I'm starting to think about this one. Because I could write an exponent in. 9x to the what is the same as 9x to the 0. So technically, if it's just a number, we can attach an exponent to that, just x to the 0. So that means the degree would be, the lead coefficient would be 9, the number in front of the x. Now, what about the constant? Would be 9 also. Yeah, that's kind of a weird one. Okay, so we've seen sort of what's a polynomial function and what is. So let's start looking at certain types. Ones that we've seen, ones that we haven't seen. Okay. So how do we identify polynomial functions? Says here by the degree, the highest exponent. The end behavior, what's happening on each side, the right side and the left side of the graph? Is it going up? Is it going down? Is it going straight? What's happening? The domain and range, how many x-intercepts there are, and what the y-intercept is. Now, remember, degree refers to exponent. So, if we have an odd exponent as the highest degree, okay, the ends will always go in different directions. And you're going to see, I'll see this when we do an example. The ends will go in different directions. Think of like y equals x. Y equals x goes up to the right, down to the left. They go in opposite directions. But y equals x squared is a parabola that on the ends it goes up both sides. So if it's even degree, the ends go in the same direction. And whatever the degree is, whatever the highest exponent is, that's up to, wait a minute,
sure I'm right here.
Yeah. There could be up to the exponent number of intercepts. Okay, and I'll refer back to this when we look at the next page. So here's a whole bunch. These ones, we've done. We've seen these. The bottom three will be new. Okay? This is, and I need this. I need my reference here. Just to make sure I'm not leading you down the path. If it's degree 0, we call it a constant function. Basically, it's a horizontal line. It is even degree. Notice that on the ends, it doesn't go up or down. It goes straight to the right, straight to the left. Okay? But 0, think of degree 0. 0 is an even number. How many x-intercepts could there possibly be? Okay? Well, 0. Because if you draw, besides the x-axis, if you draw a horizontal line, it'll never touch the x. Okay? I guess you could say, if it's the x-axis, if it's this horizontal line, well, then there's infinite x-intercepts, but that's an exception. So an example, what would be an example? Well, this one is actually y, or f of x equals 3. This is the horizontal line, y equals 3. The end behavior is it extends horizontally. There's nothing happening vertically. What's the domain of this one? Negative infinity to positive infinity. Well, this next one, you got to be really careful with your notation. What's the range? Just 3. Because isn't the y value always 3? And if it's just a single number, that's when we put the fancy raised. Or, I mean, technically, we could do that. That would be fine too. Because this is going from 3 to 3, including 3, which means 3. How many x-intercepts? None. What's the y-intercept? 3. So that's a constant function. Horizontal line. Degree 1 is an odd degree, obviously. Okay. What do we call this kind of function? If its graph is a line? Linear. Linear function. How many x-intercepts does this have? 1. Here's an example of a linear function. This specific one is y equals, I'm looking at the slope and y-intercept, 2x plus 1. That's the name of this one. Yes. Now it's end behavior. When we talk about the end behavior, we're talking about its end vertical behavior. So on the left side of the graph, it's going down. Okay? So extends down in quadrant 3. And up in quadrant 1. So that's going in terms of vertical direction, that's going in opposite directions, which is what we talked about what odd degree functions were. The ends go in opposite directions. The domain is everything because it goes to the left forever and the right forever. The range is everything because it goes to the left forever and the right forever. The number of x-intercepts it could have, 1. And what's the y-intercept of this specific one? 1. Next one is a second degree function, which means it's even. The highest exponent is 2. What kind of functions do we call these? Quadratic functions. This is where things, you got to start thinking a little bit. How many possible x-intercepts could there be? What are the possibilities? Could I draw a parabola that has none? Yeah, I could just draw it like that. Could I draw one that has 1? Where would its vertex be?
0, 0.
Well, it could be 0, 0, yeah. On the x-axis. Yeah, so like that. Could be right side up, upside down. For this one here, which has 2. So that means we could have 0, 1, or 2. This quadratic function is y equals x squared minus 3. Just going to erase these so we can see this clearly. What's the end behavior? What's happening on the left, up or down? And on the right, up. So it extends. Notice I read it from left and right. Up in quadrant 2 and up in quadrant 1. They go in the same direction. And that's like we said on the previous page. What's the domain of any quadratic function? Always. But the range depends on where the vertex is and whether it opens up or down. This one would be -3 to infinity. How many x-intercepts does this one have? And what is its y-intercept? So these are the ones we've done. And these are the properties we've talked about. Although we never really talked about end behavior before. All right, let's go to the funkier looking ones. Here we have a polynomial function where the degree is 3. That's an odd, obviously, because 3 is odd. Anybody know the name of it? What math word can we use for 3? Try. What about another word? That's a good guess. What's that? No. Doesn't have try in it. Whenever you, I know we haven't done this for ages, but whenever you find the volume of something, your answer is always in units cubed. Because cube stands for 3. It's a cubic function. How many x-intercepts could a cubic function? Could have 3. Well, this one has 3, so obviously, could I write one that has 2?
Yeah.
Yeah, I could just sort of take this, go like that. That one has 2. I could do one that has 1. How would I do one that has 1? I guess I would just go like this. Just go like that. It just doesn't reach the top. How about 0? No, it's always got to go through once. So this one has 1, 2, or 3. Any even degree function will never have 0 x-intercepts. Or sorry, pardon me. An odd degree function, I meant to say. That's right. Can never have 0 x-intercepts. There has to be 1. At least. Okay, so what's the name of this one? Well, this specific one is y equals x cubed plus 2x squared minus x minus 2. That's the equation of this one. What's happening on the ends? So if we go to the left side, it's down into Q3. On the right side, up into Q1. Very similar to the line, the linear function. So it extends down into Q3, up into Q1. Notice all odd functions will do that, except if we throw a negative in front, which we'll talk about later. Domain, well, we've seen a pattern. Yeah, for all of these, doesn't matter what the highest exponent is, the domain's going to be everything. And for this one, the range is going to be negative infinity to positive infinity. Because it goes down forever and up forever. This one has 3 x-intercepts, and its y-intercept is at -2. Degree 4, obviously even degree. 4 is an even number. Any idea of the name? What represents 4? How do you say 4 in French? Yeah, so it's kind of like that. Quartic function. How many x-intercepts could there be here? Could I have 0? Yes, because what if I took this whole w and moved it all up above the x? There would be no x-intercepts. And then I could drop 1 down to the x-axis and have 1. And then I could drop these 2 things down to the x-axis and have 2 or 3. Or like this one, 4, but no more. How's the 1 possible? There's an upside down one. I just didn't want. There we go. Just move one of the, I guess for lack of a better phrase, vertex points to the x-axis. This one specifically is y equals x to the 4th minus 5x squared plus 4. We should see the patterns in the end behavior now. On the left side, it's extending up. Right, it's extending up as well. And that's what happens with even degree functions. So extends up into quadrant 3 on the left and up into quadrant 1 on the right. Oh, sorry, quadrant 2. Yes, thank you. Oh. Okay. So domain, like we've seen all along, is everything. So negative infinity to positive infinity. But the range, well, the range is kind of hard to see, isn't it? Because isn't it below -2? But it doesn't get to -3. So I guess we could take a guess and say, I don't know, what's that, -2.2? Negative, like this is -2.5 here. So maybe -2.2. You're not going to have to worry about decimal. Stuff like that. This one has 4 x-intercepts, and its y-intercept is at 4. Yeah.
Like, draw around the 4 intercepts?
Can I draw around the what?
But I can't see the 4.
The 4. You got it?
Okay.
You good? Okay. Degree 5. Last one. We're not going to look at ones past this. This is obviously an odd degree. And its name is quintic. Yes, fun to say. And difficult to spell, apparently. Because it's odd, there's no way it can have 0 x-intercepts. It could have 1, 2, 3, 4, or 5. You just have to shift these things around onto the x-axis. This specific one is y, or f of x, of course, equals x to the 5th minus 5x to the 3rd plus 4x. Its end behavior is like every other odd degree function. Down on the left into quadrant 3, up on the right into quadrant 1. So it extends up, down, down into quadrant 3, and up into quadrant 1. Domain, like we've seen all along, is everything. The range of any odd degree function is also everything. Only changes when it's an even degree. Number of x-intercepts in this one, well, there's 5 of them, but the y-intercept is at 0. No, that's a lot of stuff. Okay. but come on. Oh. And the hockey players will like that. Okay, last thing we're going to look at. What happens if there's a negative at the beginning in front of the highest exponent or the degree? Yep, flips, right? So you can see here, here's x to the fourth. It forms like a W shape, okay? Like it actually, if you think about it, x squared is a parabola. X to the fourth would be almost look like two parabolas connected. X to the sixth would be like three parabolas connected. And you could also do the same thing with odd functions. Okay? Like x to the third is two parabolas connected, one right side up and the other upside down. Okay? And so on. So you see what the negative does. And you see what the negative does here. Okay? X to the third, notice, goes in opposite directions on the left and right. But if we have a negative in front, those directions change. Still goes opposite directions, but different opposite directions now. Because negative reverses everything. So just to finish up, let's look at a couple of examples. This is basically what I want you to get out of this lesson. Okay? If you're given a polynomial function, be able to state properties. That's basically everything that we've done in this lesson. So the first thing is we want the type of function that it is, whether it's odd or even. The end behavior. So what's happening on the left, up or down? What's happening on the right, up or down? The number of possible x-intercepts, the total, the maximum number. And whatever the y-intercept is. So this one, what type? 3, 4. Odd or even? Even. End behavior. And notice I go from left to right. Up and up. Up into Q2. Oh, that's weird. Up into Q2. Okay. Up into Q1. The highest number of x-intercepts it could have. 4. It's always the degree. I don't know if this one specifically has 4. We'd have to graph it to see. The y-intercept, well, we're going to have to do a little math. So we're going to have to plug 0 in every time we see an x and calculate. But it's pretty easy. Because all of these are you're raising 0 to an exponent or you're multiplying by 0. So all of these are zeros. So the y-intercept would be positive 3. I know, it's a weird looking 3. Try this last one on your own or with somebody else. Quick tick. Okay, so down a little. Now, this is, I think, the one where people got thrown a little bit. Up into 2, down into 4. Because if you think of the non-negative, it's like this, right? But the negative goes like this. That's enough for the charade. So, up into quadrant 2, down into 4. ID. Maximum number of x-intercepts? 5, And the y-intercept, 0, because if you just plug 0 in, everything becomes 0. Good.